Welcome back to the Methods Lab. In this series we study advanced data science pipelines in R and take a look under the hood. My name is Casper van Lissa and I will walk you through the code and teach you how to think like a professor of data science. The techniques you learn in the Methods Lab will help you turn questions into answers, data into better decisions, and skills into cutting-edge research projects. Today we're looking at another topic that is close to my heart, and that is computational reproducibility. The ability to get the same results from your data over time and on different computer systems. I've recorded several YouTube videos about this topic, including conference presentations and self-paced workshops, and I would recommend that you look at some of those if you want to dig deeper into the topic. But today I'm approaching it in a way that I've never done before. It's a little bit more hardcore. All of my previous videos assumed that you were just about to start a new project and wanted to make it reproducible from the start. But today we're looking at arguably a more common scenario where you have working code and you just want to wrap it in a reproducible project before you archive it. Today's video is also relevant for those of you who are not running R in RStudio. Even though that is exactly what I will be doing, I will be using mostly the interactive command line to make the project reproducible. So this will also work for you if you like to use Posit or Visual Studio or any other IDE to edit your R code. Now, I'm not going to give a whole lecture about the how and why of reproducibility, but I will give you a very brief introduction to the basic concept. There's a phenomenon in computer science called works on my machine. It happens when someone has written code that for some reason works perfectly on their machine and yet nobody else can reproduce it. For scientific research, this is a problem, because how can we trust results if they only work on your machine? This morning, I had an experience that reminded me why this is so important. I read a paper looking for a table of model fit statistics that I needed to do my research. And the table just wasn't there. And instead I found a sentence that said, "This table of model fit indices is available from the lead author upon request." Of course, they also forgot to document the lead author's email address with this paper. And when I finally did find it, it turns out that that email address had been disconnected. Now, maybe you've experienced similar situations where you thought this information should just be accessible, it should just be easy to reuse, and it wasn't. Let's commit today to try to do better and learn how to generate reproducible projects ourselves. So what makes a project reproducible? Well, very simply put, a reproducible project should have a clear entry point, so that's where the user starts interacting with the project. And then it should have a well-defined computational recipe, this is typically R code if you're working in R, that generates the output, and to be reproducible, that generated output should be the same as the output that you archived at the time of publication. But how do we get there? Well, basically you need three things. One is, instead of writing a document in Word and copy-pasting output from statistical software into that document, you should be using a dynamic document format. And this could be R Markdown if you're working in R, or it could be a Jupyter notebook if you're working in Python. And basically these kinds of documents combine written text with analysis code so that the results in the text can be automatically generated from that code. This makes your paper easy to update, and it also means that the unit of reproducibility is the paper source code itself. So you can check if the project reproduces by recompiling the paper. If the paper is identical to the published version, then voila, you've reproduced it. The second thing that you will need in order to make your papers reproducible is proper version control, so that it's always clear which version is the version of record that people should be trying to reproduce, because there are always many changes made. So if you're able to reference a specific version of your project, it will be easier for people to match up the reported results with the reproducible results. And finally, an important pillar of reproducibility is dependency management. When people first started thinking about reproducibility, they focused on data sharing and code sharing. But the problem is that the same code is not guaranteed to give the same results, even if it's run on the same data, because code depends on software to be executed. So you also have to document the exact software environment that was used to generate the results from the code and the data. So again, to sum up, for reproducibility, you need 3 pillars: dynamic document generation, version control, and dependency management. Now, all 3 of these pillars are taken care of by the worcs R package. Worcs is short for Workflow for Open Reproducible Code in Science, and that's the package we'll mostly be using today. The end goal of our workflow is to archive our reproducible research project in a fair way. FAIR is an acronym that stands for Findable, Accessible, Interoperable, and Reusable. Findable means that it's archived in a place where people are likely to look for it. For example, in my field of psychology, people tend to look on the Open Science Framework, osf.io, but in other fields, people tend to look on Zenodo. I like Zenodo. It's a perfect archive for making research output fair. And thankfully, it interoperates with the Open Science Framework, so you can archive on Zenodo and then link that archive to an Open Science Framework page, and you've got your bases covered. And a FAIR compliant repository like Zenodo will also give you a DOI for your project, short for Digital Object Identifier. That is a permanent hyperlink where people can find your repository. Accessible has several interpretations, but the most important property that I like to focus on is that all files should be human and machine readable. So I like to use different plain text formats. Interoperable means that people can reuse and build on your repository. One way to achieve this is by using only open source software, so people don't need to go through a paywall before they can interact with your project. And finally, reusable means that people are legally and practically able to reuse your project. And one way to achieve this is to give your project a permissive license. If you don't license your project, it is copyrighted and people are strictly prohibited from reusing it. So if you want people to build on it, you should give it a license. The CC BY license, Creative Commons Attribution License, is most compliant with citation practices in academia. Although for some resources, you might want to waive any copyright claims with a CC0 license. And this just means that people can reuse your project at will, even without attribution, but you could still remind them that it's good scientific practice to cite you anyway. Now you might be thinking, this all sounds like a lot of work. Why would I ever bother to make my project reproducible? And there's actually a very good reason for it, even if it's a project that's never meant to leave your personal computer, or if it's a proprietary project in your lab or your company. And here's the reason. Making a project reproducible is a way to be kind to your future self. Think about it like this. If you just work on the code locally, don't make it reproducible, your computer system is going to change over time. You're going to update packages, delete some software from your computer, install new software. And if you ever come back to that same project, the code might no longer work because the software dependencies around it have changed. Making the project reproducible prevents this because you can always come back to a kind of time capsule where all of the old dependencies are still documented and your code runs as it was originally intended to run. And this also makes it easier to share it with a neighbor in a next door office or with a collaborator or a line manager. And eventually, yes, it does make it easier to share it with the whole world, but you don't have to. So making a project reproducible has benefits even if you never intend to share it with the whole world. It makes it easier to come back to that project and interact with it later. Or to duplicate it and start a new project based on a working old project, not some broken code. Okay, so I hope I've convinced you why reproducibility is important. Now let's set a goal for today. And the goal is that we're going to take some working analysis code that we wrote together in a previous installment of the Methods Lab where I explained how to do latent class analysis with mixed indicators. So we're going to take that analysis script and turn it into a reproducible archive. Now, because this code is super compute intensive, I'm going to add some special sauce that prevents us from running redundant compute, and that is the targets R package. So in order to create this repository, I actually have to connect to a more powerful supercomputer to run the code because my laptop is really too slow to do it live. The first thing I do is navigate to this GitHub page where we archived the results of last episode where we conducted latent class analysis. And I want to get this code onto my local computer. So I click here on code and I select this URL, copy paste it. I'm going to go to a local folder and here I'm going to open a terminal and I'm going to git clone and paste this URL. And that should clone it into that folder. So we close the terminal again and voila, here we have a local copy of this archive. So let's open RStudio, and if you prefer to work in another IDE, that is fine too. And the first thing I'm going to do is install.packages works, because that's the main package that we'll use to make this project reproducible. Now, having works installed gives us a project template if we make a new project. And in previous videos, I've explained that you can create a reproducible project by going through this wizard, the new project wizard, and selecting the works project template. That's not what we're doing today. Today, we're going to take an existing repository and make it reproducible from the command line. So basically, we're going to turn this R project into a works project, and we do so by calling the function works project. Let's have a look at the documentation for this function. So we need to specify the path to the project. We can specify a manuscript template, a pre-registration template. We can add a license. We can use renv, and renv is the package that handles dependencies within an R project, so this is super important. We can also use targets, and like I prefaced before, this is a very compute-intensive project, and targets helps us deal with compute-intensive R code, so we're also going to use targets for this project. Then we can connect it to a remote repo, that is a GitHub repository, and we can make it verbose or not, which gives us status updates. So here is how I'm going to specify these arguments. The path is going to be the current path, indicated by a period. The manuscript template will use a GitHub document. We do not need any pre-registration template, so we set that to none. The license is good, so I'm not going to change that. The renv argument is set to true by default, so we keep that. But we will override use targets, set it to true. And we use the argument remote repo, and we'll call it demo reproducibility. So that means that after I run this code, there will be a repository called demo reproducibility on my GitHub page where you can fork it or clone it and play around with the code yourself. I think that's all we need. Let's press enter and run it. So you get the status updates. It initialized a Git repository. It wrote a works file where some metadata is stored. It copied some boilerplate files, created a manuscript, added a reproducibility recipe. Okay, the license is not correct. I see why. Yeah. And it's linking package dependencies. So you see we already have 158 package dependencies. I like to make my projects reproducible with as few dependencies as possible because every dependency is a liability. In this case, we weren't very fastidious about that when we made the original code, so we have a lot of dependencies. But it's just something that you might want to think about. This, by the way, is one reason to prefer base R over tidyverse, because tidyverse inherits a lot of dependencies. Okay, so we had one warning and one error in the process. And as per usual, I show you the dirty work. Let's debug these errors. First, let's deal with the warning. We saw that the default license argument does not correspond to any license in use this. That's actually something that I should debug, shouldn't be your problem. But we can fix this by using the function use this, use some kind of license. So let's run that. If we run the function use this, use cc by license, Then it adds a license.md to the folder. Let's verify that it's there. And yes, here it is. So now we've got a CC BY 4.0 license added. The second bug that we got is that connecting to remote repository demo reproducibility failed. So that's interesting. So the first thing I would usually do is run a check to see if works is properly connected to GitHub. And that function is works check GitHub. And if we run it, we see that this project does have a remote repository and it requires personal access token authentication. I do have a personal access token correctly set up, so this shouldn't be the problem. So let's have a quick look and see the Git status. Okay, so it looks like this is also a Git repository and the following files are being tracked by Git, which is our version control system. The second thing we can check is whether the GitHub remote repository is connected to this local repository. We can use the function git remote list. And I see it's still connected to the previous GitHub repository because this already was a GitHub project. Okay, so we just found the source of the bug. I took an existing Git repository with an existing GitHub remote address and I tried to push it to a new GitHub remote address. That's not a good idea. So to fix this, what we're going to do is git remote remove, and we're going to remove the original one, which is labeled origin. And now if we do git remote list, we see there's no more remote repository. And now we should be able to do works git remote connect, and we're going to connect the present directory to the remote repository, which we called demo reproducibility. Let's try that. And now that works. So now if we again check git remote list, we see that the new correct repository is connected. And with that, we can push all of our local files to GitHub. We can use works git update, and we call it first commit, and boom, everything is on GitHub. So let's verify that. So we go to demo reproducibility, and indeed here is our archive. And note that we now get a nice works project label, which signifies that this is indeed a works project. Cool. Okay, now all the scaffolding is in place to turn this into a reproducible project. But we still need to go through a few steps. Specifically, what we want to do is to take our previous analysis script and turn that into a reproducible pipeline. And for this, we're going to use the targets package. Now, where works helps you set up a scaffolding for reproducible projects, targets prevents you from unnecessarily reproducing code that is unchanged and whose inputs remain unchanged. And this is useful because when you make a reproducible project, you end up rerunning it over and over again. But if your code takes a long time to run, like this latent class analysis, that is super wasteful. So to prevent that, the targets package checks for every chunk of code. Has the code changed or has any of the input to the code changed? If no, then don't rerun it. If yes, then do rerun it. So the targets package creates, do I have targets in here? Why is there no targets? Okay, so we didn't actually get targets for this project yet, but we can add it as follows. Works add targets. And we want to add it to the current works directory. Oh, that's why we didn't get it. So here's another bug. We were trying to add targets to our works project, but targets is not installed. So let's first install targets, and we also install T archetypes or tarchetypes. So we run both of this. Yes, we do want to add that. Yes, we do. So these are both installed now. And then we run works add targets. Most importantly, what we see is that this underscore targets.r file has been created. So let's open it. And it contains a lot of comments that walk us through the process. But basically, what you do is you create a list of named targets. And then for every named target, you specify a command that is used to create that target, and the arguments to the command track its dependencies to other targets. So in this case, for example, there's an object called model, which is created by running the function coefficients of lm of y on x using the data object. And the data object is created over here. It is created by making a tibble, which is a kind of data frame. So what targets will do is it will keep track of the dependency between model and data. And if data has changed, then this command will be executed again as well. But in this case, we don't need these two objects. They are just there for demonstration purposes. We're going to replace those with the code that is in our runme file, which specifies the latent class analysis that we did last time. So the first thing we're going to do is manage our package dependencies. We're going to move these over here. And then where targets likes to have them is over here in tar option set. So we see that it already says tibble is a package dependency, and we're going to put our package dependencies there. I also just like to put them here because that helps renv track them as well. But let's put them here. Let's put tidy sem, foreign. Actually, we don't need foreign. That was used to read SPSS data, but now we have some nice simulated data. So we can remove that. OpenMX, yes, we do need that to estimate the models. Psych, we need to do psychometrics. And Lavan, latent variable analysis, we also needed to do psychometric analyses. Okay, so that's our dependencies handled. And maybe to keep track of the changes that we're making, we can just delete stuff here if we've ported it over to the targets file. That'll keep it nice and clean. So what we see here is that the first thing that happens is we create an object called df, and we create it by reading data from a file. Now that is a perfect unit of analysis to put in our targets pipeline. So what we're going to do is we're going to create a new target with the name df, and we create it by running the following command: read.csv from data.csv with strings as factors equals false. Okay, just to get the hang of this, let's reproduce our pipeline with only this command. So we comment out the rest, save this file. We can also save runme, it doesn't matter. And now let's get into the habit of reproducing our targets pipeline. And we can do that either by running the function targets tar make, or we can run the works function works reproduce. So we get some update here. We see that the target df was dispatched. It took less than a millisecond to complete, and then the pipeline was finished. Now if we run works reproduce, then we see that it tries to execute the pipeline, but it skipped the pipeline because the only thing being created is df, and df was already created and it's unchanged, so the whole pipeline could be skipped. And it tells us that no endpoints were found in the works project, and that is true. So you can indicate what the reproducibility endpoints of your project should be, and then this function works reproduce will verify that after reproducing the analysis, all of those endpoints remain unchanged. Okay, now let's just port over some more code to the targets file. So one thing that's being done is that a scales list is being declared to indicate which items belong to which scale. That's also something that we can easily add to a target. So we make a new function called target name equals scales list. And the command is just this. It's just calling a list. And then why don't we keep on going? So here I see that some items are being selected from object df. Now I think this is something that we did when we loaded the data from SPSS, but now we're working with a cleaned data file, and I think we don't have to do this anymore. But just to verify that, we can use the function tar load and load df into the environment from the targets store. And then we can see that the names of df, they correspond to what is being selected here. So we have all of the items that are in scales list, right? That's the unlist scales list. And then we have the motivation items that's being declared here. And then we have frequency and sex C. So actually what's being achieved by this code here is no longer necessary, and we can just delete it. So the next thing that happens here is that a bit of psychometrics is being done, and some mean scores are created for the scales in scales list. And then we select for the latent class analysis only the scale scores. So this is actually something that we can do in a function. So we take this block of code, let's turn this into a function, and what should this function ingest? We say make scales. It's a function that ingests the df argument and the scales list argument, and then it performs these operations, and it should return df lca. So what happens inside this function? First, we perform psychometrics for each scale. We put that in a table, and as a side effect, we write that to a file called tabscales.csv. So technically, we could break out that step to its own function and then track the name of this file as the target for targets. But in this case, we're just going to make it a side effect of the function. That's a little bit sloppy, but in this case, I think it will be okay. And the main thing that's being created in this block of code is a data frame with only the scales list items. So let's save this file to the folder R, and we just name the file makescales, which is the name of the function. So why am I documenting this in the R folder? Well, because the function tar source runs all of the R scripts in the R folder, and that loads my custom functions into the environment. So now I can make a new target, which is df lca, and I get df lca by running make scales on df and scales list, and remember this tracks the dependencies. So if I now run targets tar make, then it should execute this target and this target. Let's go. Okay, so we get some kind of error. Let's try to debug it, and we start debugging it here. So we need the objects df and scales list, so we can do targets tar load df and also tar load scales list. So now we have both of these objects in memory, and we just try to step through this function. So we start here. Okay, it can't find some of these functions. Maybe we wanna prefix them with a package that they're from. So we could do that. See, I already did it here for SEM tools, which I forgot to declare in my dependencies. So I'm gonna add that now. So we also declare SEM tools here. And we can load it here. Let's try again, see if that fixes it. Okay, actually it might have fixed it. So now we should have an object SCLS that we should be able to row bind into a table. That's a table, that's correct. Then we're going to save it to a file. And then we should be able to get the row means of these scales. That also works. And then we should be able to select those columns from the data. This all works if we run it interactively. Let's try to rerun the pipeline and see if the bug is fixed. Okay, this still didn't work, so I'm gonna search for this error on DuckDuckGo. So the error was unimplemented type list in encode element. And what we see is that on Stack Overflow, people have asked this question. And the answer's pretty lucid. Specifically, when I try to write the CSV file, some of the columns might be matrix or in our case, list. And we see several solutions here. So someone turned the whole thing into a matrix and then wrote it to a CSV. And other people first turned every column into a specific data type. Which one do I like? Well, maybe we try to do it as matrix. And then we try to rerun it. Yeah, okay, that fixed it. So just to understand the error is that my function call here gave us some columns in the data frame that were of a type that couldn't be written to a spreadsheet. So by changing the data type to a matrix, it did work, and that's great. Now also notice that the psychometric analysis produces some warnings. If we don't want that, we could wrap this whole thing in suppress warnings. We do it like this. We can do that by moving this block of code inside of suppress warnings. And this is purely cosmetic. In this case, I know that the warnings are not important because I've already debugged this part of the code in the previous episode. So this will just make our terminal look a little bit cleaner if we rerun the code. And voila, no more warnings. So in the previous tutorial, I explained that I had a very basic approach to avoid rerunning the code, which is that I checked if the file containing the results already existed. If it didn't, then I would run the code and create that file. And if it did exist, then I would load the file into memory. So now we're going to take this and replace it with something else. Specifically, we're going to create a target with the name of reslpa. And the command to get it is we run mx profiles on dflca with the argument classes 1 through 6. Also note that I had set a seed here. And in principle, we can do that for the whole pipeline over here. If we want to set one global seed, however, we have to make sure that we run the whole pipeline in one go instead of running individual bits of the pipeline separately. Otherwise, they might jump into the random number generator at a different point. So if we want to keep using a specific seed, then we could do this. And now the seed is set just before we call mx profiles. So this took a bit longer, almost 4 minutes, even on my fast computer. So I went and had a snack while this was running. And now we can basically put all of the rest of this into the pipeline. So I'm going to do 2 more things and then we'll call it a day, because I think you get the point. So one of these things that we're going to do is we're going to make a fit table. So make a function make fit table, and it ingests reslpa. So we put this here, and it runs tidy sem table fit, writes the resulting table to a spreadsheet, and returns it. So writing it to a spreadsheet is a side effect of this function. And we can save that to a file if we like. And then there are a bunch more analyses, but I'm actually just going to skip them because the point of this workshop is to make it reproducible, not to actually rerun all of these analyses. So I'll save this to here. So I'll also name this after the function it contains, make fit table. And then I'll close these files. Okay, so what I can do now is get the tab fit object. And how do I get that? I get that by running make fit table on reslpa. So if I run this pipeline, that should be the only step that it performs. And we can have a look at that table by loading it from the target store. And then we can open it in the viewer. and that is the same fit table that we got in the previous episode for the latent class analysis. Okay, so this is how you make a reproducible pipeline with the targets package. Finally, we can render a manuscript that, for example, shows these results in the text. So I'm gonna uncomment this line here, and this line renders the manuscript, so let's edit the manuscript. So in the manuscript, we can load different objects from the targets store. And in this case, we want to load tab fit from the store. And then we can interact with those objects as per usual. So in this case, how would we interact with that fit table? Well, we might show it in the document. So we make an R chunk, and there we use knit_r cable tab fit. Caption is model fit of latent class analyses. So if we run this, the manuscript is compiled. Let's have a look if it looks good. It should be here. It's a web page. And yes, there is our table of model fit indices. So far, so good. Now there's one final thing that I want to show you, and that is how to add an endpoint and verify that your analysis reproduces. There are different things that can be endpoints. One thing is you can make a file an endpoint. For example, you could make this spreadsheet your endpoint. But I think it's a little bit more interesting to add integration tests as your endpoint. An integration test checks whether specific conditions are met, and if so, the test passes, and if not, then the test fails. And we can do it like so. We run the works function add testthat. So first we have to install testthat. Yes, let's do it. And now we have testthat installed, and it says we can call use test to initialize a basic test file and open it for editing. So let's do that. Use test, and we have to give it a name, and the name can be check reproducibility. And here is the test. So the basic test checks that multiplication works. That's a bit boring. What we can do, for example, is load that fit table, and note that because the test lives here in tests, testthat, here's my test, whereas the fit table lives 2 folders down. I have to access the file like so. So 1 folder down, 2 folders down, and there load tab fit.csv. So let's load it into our environment now. So one thing that we might want to check is that the log likelihood of the models is approximately the same if the analysis is reproduced. Now, why do I say approximately? Because this is an analysis that depends on random number generation. But even if we set a random seed, the exact value of the log likelihood might be different in the 10th or 16th decimal on different computer systems because they round numbers differently. So what I can do is I can take these log likelihoods that we just produced, and I can check that they are identical to the reproduced log likelihoods within some tolerance. So right now I'm gonna put those log likelihoods into my clipboard. This works on Windows, but not on Linux. Don't know about Mac. I can paste them here, and then I can write a test, expect equal tab fit $log likelihood should be equal to these. Tolerance is 0.001, so in the 3rd decimal. So these should be equal in the 3rd decimal, and that test passes. And I can name this test. So for example, I could call this log likelihoods reproduce. And if I save this and I run works reproduce, then it's going to first call tar make and rerun my pipeline, and then it's going to check that these tests pass. It tells me no endpoints found in works project. That's correct. First, I have to indicate that these tests are now an endpoint. We can use the function works add endpoint. And if we look at the documentation, we see that we can either track specific files as endpoints, Or we can say testthat to add a folder of integration tests as endpoints. So that's what we're going to do. And what happens if you use a specific file as an endpoint is that whenever worcs reruns your analysis, it will check that that file is byte identical to the previous file that was tracked in the metadata. If it's not perfectly identical, it will fail. Now, there are actually reasons why an analysis that generally reproduces could still produce a failure here. For one, because some operating systems use different rounding rules for floating point numbers. So if a number is not exactly identical in the 16th decimal, for example, this might fail. Now that's where a testthat suite really shines, because testthat allows you to test for approximate equality. So that's why in our test, we're checking that the log likelihoods are approximately the same as the previous log likelihoods with a tolerance of 3 decimals. So again, we're going to add endpoint testthat. And then if we run worcs reproduce, it should first call tar make to rerun our pipeline. And then it will run the test suite and check if the tests pass. And indeed, that does pass. Now there's a major caveat here that even though tar make was called, none of the steps in our pipeline were rerun because they are all up to date. So if someone else runs this on a system where all of those targets have not yet been created, then it will actually reproduce the analysis. But why don't we verify that? So the first thing we do is we back up everything that we've done to GitHub. So I'm going to use the function worcs git update, and I will say first reproducible version. And then I'm going to switch to my laptop and just try to reproduce this analysis. And this is extra nice because my laptop runs Linux, whereas my supercomputer runs Windows. So we get to check cross-operating system reproducibility. How cool. So the first thing I'll do is I'll navigate to the new GitHub page with the demo reproducibility project, and I'll get the link to clone that onto my Linux computer. I prepared a folder here and I will open the terminal, and there I will just run git clone and then clone that repository. And here we have it. So now on my laptop, I can open the R project, and I just realized that I forgot to do something. Did you think of it? I forgot to snapshot my R packages with renv. That means that the package versions that I used on my supercomputer are not properly tracked, so my Linux computer might not have access to the same R packages. Let's go back and fix that. So to snapshot the package dependencies, I will call renv snapshot. Yes, I want to proceed. Yes, I want to add these to the renv file. And we see that the renv file was now updated. So I can worcs git update snapshot renv, push that to GitHub. And then on my Linux computer, I can git pull. And now I've got the latest version of the packages. So let's go ahead and renv restore those. So if you were to clone this repository and try to reproduce it on your computer, you should also first run renv restore to install all of the package dependencies in their proper version. And this is documented in one of the tutorials in the works package. Okay, so here we have all of the packages restored in their correct versions. So that's dependency management taken care of. And it asks us to restart the session. Let's do that. And basically now we should be able to run worcs reproduce. Okay, so we see that it's recreating df and scales list and df LCA, and now it's dispatched res LPA. And that's the latent class analysis, which took 4 minutes to run on my supercomputer. So let's see how long it takes. Here, it took almost 18 minutes, so quite a bit slower. And we see that the endpoints are checked and that the tests pass on this computer as well. In other words, we made a reproducible project that passes integration tests on a new system. You can even set up GitHub Actions to reproduce the project and run integration tests for you. I'm not going to show you for this project because GitHub Actions charges by the minute, and if you have a very compute intensive project like this one, you probably don't want to be reproducing it in the cloud. But for a very basic project that just consists of some regression analyses, that's probably fine. So let's sum up what we learned today. We learned about the basic pillars of reproducibility. We learned why reproducibility is important. We took an existing R project and ported it to become a fully reproducible works project with targets to reduce redundant compute. We then pushed that reproducible archive to GitHub, cloned it on a different computer, reproduced it there, and passed the integration test suite. One final thing that you might want to do for your own projects is to take this GitHub repository and archive a static copy on Zenodo or the Open Science Framework. Both of those platforms interface with GitHub, so it's not too difficult to set that up, and also it's very well documented elsewhere, including in the works package documentation, so I'm not going to get into that right now. But I recommend you to either download the GitHub repository for this demonstration and play around with it, or to apply all of the steps to one of your own projects to make it reproducible. Now, if something doesn't quite make sense yet, that's fine. Just see how far you get. If you have any questions, post them below the video or hit me up on LinkedIn. And if you have any suggestions for future videos, then let me know. This is Casper from the Methods Lab, and see you next time.